Okay, for these first couple, remember that they're asking for all of the square roots. This little symbol right here, when you see that, it implies principal square root, even though we usually just say square root. But when they ask it out, in words right here, we're not only taking the principal square root, we're taking the negative square root as well. So the answers for the first one, the square roots are 10, because 10 to the second power is 100, but so is negative 10 to the second power. If you take negative 10 and you square that, you do get 100. So the answers are 10 and negative 10 here. For this one, the answers are, be careful with the decimals, 0.7 is one of them, and so is negative 0.7. So you could also write that shorter by just doing plus or minus in front of a 0.7, but just stressing that it's both a positive and a negative answer for these. All right, for these, remember the number part you can use your calculator for, but you got to understand the properties when you're simplifying the variables. So I like to separate those into two different cases. So for the number part, you got square root of 36. That's just 6, and this is the little principal square root sign, and then you got square root of x squared. Now, because you have a even root and there's x squared, the solution to this one's going to be absolute value of x, because there's like it could be a negative that's squared to be a positive, so you could end up with even though the x is negative, the result no matter what is going to be positive, because you could be squaring a negative right here. And then square root of 36, that should be something you shouldn't even have to take your calculator out for. That's just 6, so you get 6 times the absolute value of square root of x. For this one, we don't have to worry about absolute values, because when you have a cube root, it preserves whatever sign you have. So if the radicand is negative, it's going to output negative. If the radicand is positive, it's going to output something positive. So again, separate the numbers either mentally or actually writing them out. I know that 2 is the cube root of 8, so I know that the answer should be something with a 2, and so it's going to be 0.2 here. It's going to be what the result is. And then the cube root of y cubed is going to be just y. Remember, the shortcut is divide the exponent by the index. The cube root of x to the 6 is going to be x squared, because 6 divided by 3 is 2. So you get 2/10 times y times x squared. Some of the square roots are not going to be simplified into perfect squares. So for instance, square root of 50, you can prime factor 50 and you get 25 times 2, and then 25 breaks down into 5 times 5. So there's 2 5s, so 2 5s make it out, but I choose to see it this way. Square root of 25 times square root of 2. I know that square root of 25 is 5, so this is going to be 5, and then square root of 2 for that one. The 2 stuck inside the radical, the 5 breaks out. And then for these right here, for the x fourth and y to the eighth, remember the shortcut is there's an invisible 2 right there in the index because it's a square root. 4 divided by 2 is 2, so you're going to get, let me get more room here, you're going to get 5, you're going to get an x squared, and then 8 divided by 2 is 4, so you're going to get a y to the fourth. Because those are even numbers inside of an even root, it makes sense that there would be absolute value symbols right there. But if you at least understand that it's 5x squared y to the fourth, like, you're in good shape. And really, if since the instructions don't specify to put absolute value symbols, and really I'm not gonna require it anyway, it's just a really trivial distinction. Just 5x squared y to the fourth, that's a perfectly fine answer. All right, for number 6, again, 32 is not a perfect fourth power, or maybe it is, I don't know. But for sure, if you take 32 and let's prime factor that, that's 2 times 16. 16 is 2 times 8. 8 is 2 times 4, and 4 is 2 times 2. So we have 5 2's altogether. So I'm going to choose to see that as, first I'm going to write 4 the 2's, then there's one more 2. So if you fourth root that, put the little 4 out here, this 1 2 makes it out. So you end up getting a 2 on the outside of the little fourth root here, and then you get at least 1 2 stuck on the inside. Now let's look at the variables. 7 divided by 4 is 3. So off on the side here, I'm going to take 7. You can do it mentally too. 7 and divided by 4. So that's 1. And then remainder 3. So the idea is that one of the m's makes it out, and then 3 of the m's remain inside the radical. Okay? And let me give myself some room to move this right the right. Okay, so let's look at the ends now. For the ends, remember the shortcut is to divide the exponents. You have n to the 9th, and it's inside a 4th root. So there's 2 sets of 4 in there. So you get, when you divide, you get a remainder of 1, just like before we got a remainder of 3 and we put the exponent 3. You get a remainder of 1, so I don't need to write this 1. You can write that 1 or not write it. So you could put the n with the 1 power, but I'm going to choose not to write it. Whereas on the outside, since 2 n's made it out, I am going to put an exponent of 2 on the n out here. So you get 2mn times the 4th root of 2m to the 3rd n. So that's your final answer. For the next one, we have to multiply and simplify. Now, there's 2 ways to really look at this. You can actually simplify first sometimes and then multiply, but I'm going to do the first one, the first way they suggested, which is multiply then simplify. Commutative property can be really useful for this. So the 6 and the 2, notice how those are just constants hanging outside. So write your little coefficients of your constants hanging outside. And then the 4x squared, and then the 9x squared, y squared. Put those outside, put those together inside their own radical. And you can multiply 9 times 4 and get 36, but I just so happen to notice that 9 and 4 are both perfect squares. So joining the 6 and the 2 outside that are multiplied together, you're also going to have the 2, which comes from square rooting the 4, and you're going to have a 3, which comes from square rooting the 9. And then I also noticed that, this x squared right here, that could be an x, and then this x squared right here, that's another x, and then this y squared here, that could be a y. So actually everything makes it out of the radical, and you just have to multiply these coefficients together. So you get 72. Sorry about that. You get 72x squared and then y. Now technically the y will be in absolute values, and here's the difference between uh, the x and the y. The reason you don't necessarily have to put the absolute values around the x squared, like there's no reason to put it because, well, when you square x, it's going to be positive anyway. So if you look at a previous example that like this one right here, see how I put the absolute values right here? Well, there's no need for the absolute values because when you square an x, it's going to be positive anyway. So it's kind of pointless to have those absolute values because it's already going to be positive because there is an even power here. Whereas if you go, if you had it for something, for example, let me just give you a really easy example. If you had to square root x to the 6th, you would want to put the absolute values around the x to the 3rd, because when you raise them to the 3rd power, if it were a negative, it would end up turning it positive. It would preserve negativity. I mean, so like we would want to put absolute values around like odd roots, but you don't necessarily have to do it around odd powers, but not necessarily even powers. But anyway, this is your answer: 72x squared times y to the 1st power, but that y to the 1st power could be an absolute value. For the next one, instead of multiplying first and then simplifying, I'm actually going to just prime factor these. This is 3 times 3, that's 3 times 3. Now keep in mind these are in cube roots, not square roots. So I can put these all under the same radical. If I treat them as like they're under the same radical, see how there's 3 3's? So that means 1 3 breaks out of the radical, but the remaining 3 gets stuck inside the radical. Another way you could see this is 3 to the 4th inside of a cube root. So you can do that little division of exponents trick. Either way, you get a 3 outside of a, make sure you write cube root, it's not a square root, and then the 3 stuck on the inside. That's your answer. All right, the next one is a practice with a fourth root. Now, if you don't have it memorized, the fourth root of 16 is just 2. So, 2 times 2 times 2 times 2. So that one's real easy. For the x exponent, just divide 8 by 4, so you get x squared. There's no need to use absolute values because when you raise it to the second power, even if x was negative, it will become positive, so there's no point in putting absolute values there. And if you look at this right here, if you raise something, let's assume that x was negative here, you'd be raising it to the to an even power, so it would turn it negative. But either way, don't focus on the absolute values if that's something you're still not super clear on. But at least get the rules right. If you take 14th power and you want to divide it by 4, that goes into this 3 times, and so you get 3 remainder 2. So that means that inside of this fourth root, there's going to be 2 x's stuck inside of the fourth root, but there's going to be 3 x's that are going to be hanging out right here. So you got 3 x's, and then you got 2 x's. Oh, that means altogether we got 5 x's hanging outside, and then these 2 x's are trapped inside of this fourth root right here. And so we get this as our final answer, the 2x to the fifth, fourth. And so notice this, like you may have thought like, oh well, x is to an even power here. So like it's not gonna matter what you get. You're not gonna have to worry about absolute value signs either way you cut it. So I'm gonna try to be more clear on that. But since right here the x is raised to an odd power, like even though we have that, we don't need to worry about having absolute value. Now, this can actually go one step further, though, and we're going to do this by writing this in exponential form. So this is because we have x to the fourth, and then like fourth root of x, and there's x squared in there. Let me rewrite this part right here. This is x to the 2/4 power. Now, instead of writing 2/4 power, this can actually be reduced. Even though you can't like break all the x's out, x to the 2/4 power is the same thing as x to the 1/2 power. So instead of writing fourth root of x squared, we could write just square root of x because that radical actually reduces. So a similar situation might be if for some reason, yeah, you won't, but say you had a sixth root and there's an x to the third in there, that it would be the same thing as x to the 1/2 power, for example. When you're dividing, similar to when you're multiplying, remember that the root, if you're dividing two things with radicals in them, it's the same thing as just dividing them first and then doing the radical, so it works out. So I like to think of these all underneath one radical, so 36x to the fourth, and then 9x to the sixth. So first I divide them before I even do anything with square roots. Even though you can square root 9 and square root 36. Square root 36 first, you get 6. Square root 9, you get 3. That works out just fine, and that reduces to 2. But it also works out this way. 36 divided by 9 is 4, and then the square root of 4 is 2. So either way, you get 2 right here. And then remember the rule when you're dividing two powers at the same base, you got to subtract the powers, but you get x to the negative 2. Well, what's x to the negative 2? Instead of seeing it that way, you can see that there's 6 x's, that's more than the 4. So you get 2 over, and this is still inside the square root, the square root of x squared. Well, the square root of x squared is just x, so you get 2 over x right here. And since this is even an even power, like inside, and then also you have like an odd power outside, it makes sense that we could have that as absolute value. For the next one, these are definitely these are both cube roots. So again, I'll solve this one the other way. You could focus on just the top. So the cube root of 64 is a nice number. It's 4. The cube root of x is 9. The trick is to divide the powers. 9 divided by 3 is 3, so you get x cubed. 3 divided by 3 is 1, so there's only one y to the first power. The cube root of 8 is 2. Take this 3 power and divide it by this index 3, you get 1. So we get this right here, but this could be simplified. 4 divided by 2 is 2. X cubed divided by x, you subtract the powers. 3 minus 1 is 2, so you get x squared. And then the y is hanging out right there. And we're dealing with a cube root right here, so there's no need to even consider using any absolute values, but this is your answer. For number 12, we're practicing rationalizing, simplifying, and if needed, rationalize denominators. So we're adding and subtracting radicals right here. You have to have like terms. It looks like you can't do anything with this, but you have to reduce, you have to simplify the radicals to see if you really can combine these. So let's look at 81. That's 9 times 9. And then each of those break down into a couple of 3's. So really, the cube root of 81 is, let's write the 10, that's just hanging out. And then 3 3's break out, so it's times 3 and then cube root of 3 inside. So that's really 30, because it's the 10 times 3, 30 times cube root of 3. All right, and then the square root of 24, again, you could prime factor the 24. 24 is 6 times 4, and then 6 is 3 times 2, and 4 is 2 times 2. So 3 2's break out of that. So you got the h just kind of hanging out, times, then you have 2 on the cube root of 3. Hey, it's cube root of 3 both times, so these actually are able to be combined. So, oops, didn't write the 3 here. Got bad stylus today. 16 cube root of 3. Now these are like terms. So this is like 30 potatoes minus 16 potatoes. So 30 potatoes minus 16 potatoes, or you can think of it as 30x minus 16x. Think of it in terms of like terms algebraically. So we're going to get 14 cube root of 3. So make sure you reduce first, and usually if you reduce, the terms can be combined. All right, for number 13, we have we have it already like simplified pretty much, but it's not a rational denominator. Rational denominator means a denominator basically with no square roots. So when you have a binomial radical expression, what we want to do is multiply the bottom by the conjugate. The conjugate of 4 minus root 12 is 4 plus square root of 12. So you got to multiply by that on the top and the bottom. So multiply both sides by 4 plus square root of 12 here. And the bottom, it's really easy. You could do that little shortcut. You could follow the whole thing if you want. But the bottom's going to come out to 16, which is the 4 squared, and then minus 12, which is what square root of 12 times square root of 12 is. The top, I'm going to FOIL. I like to use the rectangular method. 4 plus square root of 12 right here. Put another 4 plus square root of 12 right here. And then do little boxes. We get 16. This is 4 root 12. There's another 4 root 12. Then there is just 12. And so the top becomes 16 plus 8 square root of 12 plus another 12, and it just so happens that the 16 and 12 can combine. So you get 16 and 12 make 28 plus 8 square root of 12. 16 minus 12, the denominator is 4. And then you can cancel out 28 divided by 4 is 7. 8 divided by 4 is 2. So your final answer is 7 plus 2 square root of 12. And that's a rational denominator because there's no square root in the denominator. But I noticed that square root of 12 is a kind of big number. So just to make sure that's reduced, let's see. If we look at 12, we could prime factor that, or we could just factor it into 4 times 3. So that's a 4 and a 3. Well, 4 is a perfect square. So 2 square root of 12, and I could have simplified the radical from the start. 7 plus, there's the 2, but then square root of 12 is square root of 4 times square root of 3. So that's 2 square root of 3. So this is actually 7 plus 4 square root of 3. That's your final answer if you reduce. That's right. For the next one, we want to make sure to reduce the radicals. Again, so square root of 48, you can prime factor the 48, but I know that 16 is a divisor of that. So that's square root of 16 times square root of 3. That comes out to 4 root 3. 27, I know is 27 is 9 times 3. So I know that that's going to be 3 square root of 3. So hey, shocker, it simplifies to something with a square root of 3 in it. And then square root of 25, I know that 25 divides that. So it's 25 times 3. So this is going to be plus, now I'm going to write the 2. And then I'm going to have, I noticed I made a mistake earlier there, 2 times 5 square root of 3. So here, see how I almost forgot the 3 that was hanging out in front? So there's still that 3 hanging out in front. In addition to the 3, this blue 3 came from here, whereas this green 3 came from there. It was already there. So we get 4 root 3 minus this is 9 square root of 3 plus this is 10 square root of 3. And then you just take 4 minus 9 plus 10, add those all together. And 10 minus 9 is 1, so 4 plus 1 is 5. So 5 square root of 3 is your final answer. Even if it looks like you can't combine the radicals, if you simplify, you usually can combine. All right, for this one, it's just practice with multiplying two binomial expressions. So I could do the rectangular method, but I'm just gonna do the little, what most people call the FOIL method here. So those two together is 3. This is plus 3 root 7. And then now distribute this, that's plus square root of 63. And then distribute this last one. That's plus, I'm just going to write it out, square root of 63 times square root of 7. Now, if I can, I like to reduce any radicals. So that number 63 is pretty big to me. So let me see if I can reduce that. That's 21 times 3, and then 3 is 3 times 7. So from the start, I could have reduced that square root of 63 to, okay, there's 2 3's and then 1 7. So that's really 3 root 7. So right here, I have, this is plus, this is 3 square root of 7 is what the square root of 63 is. And then there's another root 7 right here, which is, did this last part of the distributive property. So those actually simplify. Square root of 7 times square root of 7 is just 7. So we end up getting plus 3 times 7 on the last term here. And then these middle terms can combine. They actually happen to be the same thing. 3 root 7, 3 root 7. So that's 2, 3 root 7. So that's a 6 square root of 7. And then this 3 out front right here can actually be combined with the 3 times 7, which is 21. So we get 24 plus 6 square root of 7. We always prefer to write the constant term first because you learned about regular numbers before you learned about radicals. So that's usually why we put in this order, but you can see that we tend to always put in that order almost all the time, where we put the regular rational numbers first and the irrational terms second. Okay, this last one, it seems like there's nothing that can be simplified. Like it's just, there's nothing to do here. You can't factor down 6. That's just 2 times 3. You actually can pull out. You can simplify the denominator a little bit. So we can pull out, if you take 3 and you divide 3 by 2, you get 1 remainder 1. So actually, the square root of x, that one's just regular. But the 6 is stuck inside here, but since you do 3 divided by 2, it's 1 remainder 1, so 1y makes it out, and 1y stuck inside. It seems like we're done, but here's the thing. Remember that we're told to rationalize all denominators. Rationalize means don't let any denominators leave as a square root. So since square root of 6y is part of the denominator, I have to multiply it by another square root of 6y to turn the denominator from a square root to a non-square root. So you just multiply a root by itself. So we get the y that was hanging out there the whole time. And then you got another 6y, because square root of something times square root of that same something is just that something. Okay? And then the top, we can combine these square roots. Even though it says x, 6, and then y, I like to go alphabetical order. The number first, then the x, then the y. But all I did was write both of these underneath the same radical. And if you can reduce, you should, but nothing cancels out here. Don't do this. Don't think that you can cancel out this 6 with this 6. You cannot do that because one's a square root of 6, one's a 6. They're different things. So we end up getting square root of 6y, and I can clean up this denominator. There's two y's there, so over 6y squared. That is the expression with a rational denominator. For 17 and 18, we're just converting these into rational, from radical to exponential form. So remember that a square root is the same thing as a 1/2 power. So the negative is just hanging out front. But instead of writing square root of 17, I write 17 to the 1/2 power. You can also do, if you want, you could do, it's acceptable to do 17 to the 0.5 power. But I just kind of prefer it as write it as a fraction than a decimal. For number 8, we could simplify if we want to first. So we're just told to write it in exponential form though. So this is y to the 3 is going to be the sorry, not 3. 8 is going to be the numerator of the power, and then 3, which is where the index of the root is going to be the denominator. So we're just going to write that in exponential form, like so. I'm not going to bother simplifying. Yes, if you want to simplify, this is going to be, if you take 8 divided by 3, you do get 2 on the outside, so 2y's on the outside, and there ends up being 2y stuck on the inside. But if you write this in exponential form, that's 2y's, and this is, there's a little 3 there. This is y to the 2 2/3 power, if you write it this way. So that's just the same idea as writing 8/3. So there's no need to simplify if you just want to write it in exponential form.